improper integrals, but we only really did the skill building, which was, for the most part, how to find limits, right? So let's actually do some questions now, and we'll show you the technique that you use to find improper integrals. And we're going to focus on just type 1 today. So to remind you, a type 1 integral is one that has in either one or both the limits integration and infinity. So this is a version of question 1, and it goes from 1 to infinity, and then 3x to the negative 4 dx. So you might think, well, how do we find out what this integral looks like? What does it add up to? Well, if you visualize it, if you sketch it, it basically has that, which, to be honest, an awful lot of the curves end up looking like that one. And we're going to start at 1. And we're going to find the area under the curve forever. Now, before you get a little bit sidetracked and say, well, that's going to be infinite, because this bit at the right-hand side goes on forever. So it's obviously got more and more area. That's not always the case. Even although that curve continues to the right forever, it also gets lower and lower, closer and closer to the x-axis. In fact, in some cases, it does it in such a way that this area is actually a finite number, right? It's 42. So it is possible for these to be equal to something, right? Not all the time. When they do equal a number, we say it converges to 42 if that's the number. And if it's infinite, we typically say it diverges. The way that we get round the problem of this infinity is that we convert it into this guy. Does that, if you think of the logic of that, the integral from 1 to t, and then you find the limit as t goes to infinity. When you put those two things together, does it logically, it makes sense, doesn't it really do the same job? Agreed? 1 to t, and then you make t go infinity. So we can avoid the t, the infinite, by replacing it with t, and then later on, we'll figure out this. So the stuff that we were doing about finding limits, can you see why it's necessary? Because you're going to be finding limits all the time. In this case, t tends to infinity. So let's continue. Well, would you agree this is just basically a power rule? So you add 1 to the power and divide by the new power, and then you evaluate it at x equals 1 to t, right? Nothing too strange here. I'm kind of breaking my style point rules, and I'm going to call it that guy. Now, technically speaking, since the integral was negative powers, is it not mathematically totally okay for style points? Yeah, I'm changing into this fraction, and I'll explain in a little while why. So it's going to be the limit as t tends to infinity of negative 1 over t cubed, take away negative 1, essentially. And at this point, we're going to do the brute force. So it's going to be negative 1 over infinity cubed plus 1. Would you agree that 1 over infinity cubed is the same as 1 over infinity, and it's 0? So what do you get? You get 0 plus 1, which is 1. So this area under this curve from 1 to infinity is the number 1. And to keep the jargon correct, we say that it converges to 1 rather than saying it is 1, because it's a limit issue, right? So things converge to a number rather than equal to that number. Are we good with that? Now, why did I do this? If I had left it like this, it would have been negative, negative.
And then also I'm going to get.
Right. And can you imagine you're then going to have to do would you agree that infinity to the power of -3 is just hard to get your head around? It's hard to tell what that is. Isn't it much easier to think of it as 1 over infinity cubed? So that's the reason I did it. It's just to make the final steps a little bit cleaner, a little bit easier to do.
Why did we you use minus -1 instead of -1? If the limit's 1 to infinity.
Oh, because this expression here is -1 over x cubed. So this is technically -1 over 1 cubed. And it's top guy, take away bottom guy. So if your question is, why is that negative there? It's because of this negative here.
Oh, okay.
Are we good? First one. Pretty much that's going to be the process for all of these. We're going to take the infinity and replace it by t and then make it a limit question. So let's try this fella. Let's do the integral from 1 to infinity again. And let's do 10 over x. And if we drew 10 over x, it would look, actually pretty much look like the same guy here. So you might think, oh, well, when they look like that, the answer is always going to be a number. In this case, it's 1. Maybe in this case, it's going to be 10 or something. But no, that's not going to happen. So it's going to be the limit as t tends to infinity of 1 to t. And I'm not going to make that into a negative power because I like the way it's written already. I don't see any need to change it. What's the antiderivative of 10 over x? That would come under, I have a good memory. In other words, I just know the answer.
Is that 10 ln of x?
Correct. And we're going to evaluate that guy at x equals 1 to x equals t. And now we're going to have the limit as t tends to infinity of 10 log t, take away 10 log 1. And this question, this limit question, is going to be done by brute force as well. I don't need to do L'Hopital, right? This isn't a fraction. I can do it pretty much by just plugging in infinity. Well, actually, isn't 10 times 0, 0, but I'll do that in the next line. When you do calculations with infinity, don't you tend to get infinity or 0 as your choices? What do you think the log of infinity is? Log of infinity, what would that be equal to?
Infinity?
Yeah, so won't 10 of them be infinity? So infinity take away 0 gives me infinity. And if the area is infinite, we say that it diverges. Now, why would this one have a finite area, happens to be 1, and why will this one have an infinite area when they look so similar? It's really to do with the rate of change. What I mean by that is this function gets low, meaning close to the x-axis, really quickly, right? This one here, it's much thicker, right? It gets towards 0, but it takes a lot longer to do it. Its rate is much slower. And the difference between heading towards the x-axis really quickly and taking your time doing it is why this one has a finite area, but this one has an infinite area. Try another one. Let's do somewhere E in it. No, let's do one with a fraction. That's a good idea. This is a version of question 3. It's the integral from -infinity to -1. And it's 1 over the cube root of x. And if I did a sketch of it, it would look something like that. There would be -1, so it's this guy here. So it's going to be the limit as t tends to negative infinity this time. Let me go t to -1. Tell me a better way to write 1 over the cube root of x so that it is helpful for integration. 1 over the cube root of x.
X
I
to
want-
the power of -1/3.
You agree? Square roots get you -1/2, things like that. Now, add 1 to the power and divide by the new power. And then evaluate at x equals t and x equals -1. So what we get now? 3/2, -1 to the 2/3. Take away 3/2 t to the 2/3. And again, I'm going to use brute force. It's a very common technique. This guy here is -3/2. You can check it in your calculator, but it is. This guy here is a problem. -infinity to the power of 2/3. What is that equal to? Is it 0? Is it infinite? That's typically what you get when you do brute force. Zeros and infinity. Typically, at least. What is this one? 0 or infinity?
Infinity?
It is. Technically speaking, isn't it -infinity times another negative, which is plus infinity? This thing is infinitely large. And I don't care if it's plus or minus, it really doesn't matter, because doesn't that mean that the answer diverges? Are we good with that one? Now, if I had changed and told you that 0 or infinity now, notice I put the negative in a different spot. 0 or infinity now.
Would it be 0?
It would. You might want to write it like that. Now, does that convince you it's 0? So even something as simple as brute force, you know, how many things can happen with an infinity? Don't you have to sometimes be a bit careful, right? Because sometimes it's not that clear what kind of situation you're dealing with. Okay, let's do an exponential one now. I don't know, I think it's this version 4. Right, let's do e to the -2x dx, and the integral is going to go 0 infinity. So it's going to be the limit as t tends to infinity of 0 to t e to the -2x dx. So far, so good. I don't need to do anything. That's pretty much ready to go. If you integrate e to the -2x, you get e to the -2x times what? It's not just e to the -2x. What should go here?
-1/2.
Right? Are you all happy about that? And then you do from x equals 0 to x equals t, and move on to the next line. You get -1/2 e to the -2x, take away -1/2 e to the 0. And that shouldn't be a t, that should be a t there. So we've now got the limit as t tends to infinity. Just rewriting this because it's a bit messy. Isn't that 1? So won't that end up being +1/2? Right, time for brute force. 2 infinities is still infinity, so minus 2 infinities is minus infinity plus a half, right? Okay. E to the negative infinity, is that infinite or is that 0? E to the power of negative infinity, 0 or infinity?
I'm leaning towards 0, and I don't know why.
Well, here we go. That guy is the same thing as that guy, which is 1 over infinity, which is the 0 that you want.
My instinct was right.
Yes, you might want to play about with negative powers and rewrite them as fractions. Would you agree that when you see it as a fraction, it's much easier in your brain to see it 0? But when you see it like that, your brain's not really used to, negative anythings, and especially not negative infinities, right? Your brain just doesn't see things that way. Whereas if you convert it to its equivalent, right? Now, I don't need to worry about the negative a half. Isn't negative a half 0 still 0? And if this answer was infinity, wouldn't negative a half infinity still be infinite? So it wouldn't matter that case either. So I don't really need to worry too much about the constant. It's not going to affect the final result in any meaningful way. Are we good with that one? Any questions? So let's where are we going with this? Don't know what I want to do here. Well, let's do this. No, I've done that one. Let's not do that one. Let's do something more interesting. Yeah, let's do this one. This is a version of question 8. So that's going to be the limit as t tends to negative infinity, t to 0, x squared plus 2 to the power of 4 dx. What method am I going to use to integrate this guy? What method am I going to use to integrate this guy?
Insub?
Correct. What u sub shall I use?
X squared plus 2.
Nailed it. Are these getting easier, the u subs? You just see enough of them, you start feeling comfortable with them. Differentiate, you get 2x. Cross over. Divide both sides by 2x. And you have now finished with that. So it's going to be the limit as t tends to negative infinity. Whenever you do a u sub, leave these limits of integration out. Bring them in at the end once you've turned things back to x's. So right now I'm just going to leave it as an integral sign. It's going to be x over u squared, which is fine, times 1 over 2x du. And this is now going to be...
Would it be u to the 4th power?
Oh, well caught. Thank you. Well caught. So this is going to be 1/2 u to the negative 4 du. Are you happy about the 1 over u to the 4 turning into a negative power so that we can differentiate? Okay, so that's now going to look, add 1 to the power and divide by the new power. To make calculations easier, I'm going to rewrite this guy as 1/6 over u cubed. And now I'm going to return back to the x squared plus 4s. and put in the limits of integration. Okay, so you notice that from here all the way down to here, we didn't put in the limits because these limits would be in terms of the variable u, and we're not doing that, right? So once I get back to the x's, then I can put the 0 and the t in this case in. So time for brute force. Question.
It'd be +2, I believe, instead of +4.
Oh, me and my in a cubed. We good now? So it's going to be the limit as t tends to negative infinity. Negative, well, if you plug 0 in here, you get nothing. Nothing plus 2 is 2. 2 cubed is 8, so 8 sixes is 48. I hope I did that right. So 6 times 8. Take away -1/6 lots of t squared plus 2 cubed. So I'm going to have to do this up here. So I'm just rewriting it again. So it's -1/48 plus 1/6 t squared plus 2 cubed. Right, time for brute force. Okay, bit of a mess here. You don't need to write any of this down. I'm just going to kind of tell you what's going on. Negative infinity squared is infinity. Infinity plus 2 is infinity. Infinity cubed is infinity. 6 infinities is infinity and 0. I'd be doing all of that in my head. Are you happy about how you could just say, what would that be, and come up with the answer 0? So you do not need to do all those lines, but it does tell me that it converges. And it converges to a -1/48. And evidently that's because this shape is probably going to be below the x-axis. So that's why it's negative. So can you see you could get questions involving u-subs? They can help. Let's show you some more questions. Since I don't have enough time to do all of them, we can at least talk about some of them. And see, darn it, come on, there we go. And see what techniques that we would use to do them. I think okay, question 9. What method would I use in question 9? Just to integrate, what method?
U-sub,
Sub.
Agreed. What's the u-sub going to be?
2 plus e to x power.
Yep. Question 10. What would we use?
U-sub.
Do u-sub. Once we finish these, that's the one I'm going to do next, because it has something else in it. Do you notice that that particular question has a negative infinity and a plus infinity, right? That's like the ultimate version of a type 1, but we'll return to that later. What would you do in question 11?
Another U-sub,
And what's your u-sub this time?
x cubed plus 1.
Correct. Question 12, what would you do as your u-sub? I'm even telling you it's a u-sub. What u-sub would?
-1/x.
Correct. Actually, it comes out really nice. Could you have used 1/x if you felt like it? And that would work as well. It doesn't mean it's wrong. Just looking at 13, is that going to converge or not? If you put 13 into a calculator, it would look like a sinusoidal curve forever. It wouldn't be, it'd be a little bit distorted, but essentially that's what it looked like. Do you think that would converge if you went from 0 to infinity? No. In fact, won't sines and cosines and sine squares and cosine cubes and anything like that, don't they all diverge because they don't level off, right? They don't go down to 0. Don't they kind of just go up and down 1 and -1 or 1 and 0, whatever it might be? And any function, Trig are the most common ones to do that, but any function that does that bouncing up and down between 1 and 0 never converges. Can you imagine if you travel infinity, isn't there no stopping point? Isn't the answer going to be up and down all over the place forever? And so in a question like that, you could probably do it without any algebra at all. Couldn't you just be doing it and say, I know what that guy looks like, ain't happening, diverges. Okay, let's go back and have a look at that ultimate type 1. So if I was going to create a type 1 question that had as many things wrong with it, it'd probably be question 10. Well, don't write this down because it's wrong. But you might think, I know how this is going to work. You're going to do the limit as t tends to infinity, and you're just going to go minus t to plus t, 3x e to the negative x squared dx. Does that seem, I've told you it's wrong, but doesn't that seem reasonably logical? Right. Now you might say, well, what is wrong with doing that? Well, the problem with doing that is that this guy could cancel out that guy, and you might think that the answer is 0. Or maybe this guy is slightly bigger than that, whatever it is. And it's not allowed because what you're essentially doing is some version of infinity taking away some other version of infinity. And isn't infinity take away infinity a very dangerous place to be? We don't like infinities taking away infinities. Some quite interesting problems connected with people doing it this way and coming up with an answer that just basically didn't work. So you might think, well, how on earth do we tackle this question? Well, it seems a little bit lopsided, but this is what we do. Do you notice that what you do is you break the limit into 2 distinct pieces? And then you find the limit as t tends to infinity of this integral plus the limit as t tends to positive infinity of this integral. Now, superficially, you might think, well, that's just doing that. You're just making it look bigger, but that's what you're doing. Well, not quite. Suppose this answer is infinity. The integral diverges. Suppose this answer is infinity. The integral diverges. If one of these is plus infinity and the other one is negative infinity, doesn't it still diverge? So if either piece of it is broke, the whole thing is broke. So if this is infinity plus or minus, or this one is infinity plus or minus, then this guy up here diverges and that's the end of it. In fact, suppose we do this one and the answer ends up being infinity. Do I even need to bother calculating the other one? Right, so if this answer ends up being infinity, do I even bother calculating that one? No. If one of them's infinite, the thing is broke, right? It's divergent. And which one do you want me to try, left or right?
Left.
Left one, okay. So would you agree that we're going to do a U sub on this one, right? So let me do it over here. So it's going to be the limit as t tends to infinity of negative t to 0, 3x e to the negative x squared dx. What's the U sub? We got this question a few minutes ago, so if you want to tell me what you said last time, that's fine, but other person can join in. What's the U sub for this one?
Negative
Neg-
x squared.
Okay, so we're going to do a negative x squared. Works for me. So if you differentiate with respect to x, you get that. If you do the crossover, you get that. And if you divide by negative 2x to isolate the dx, and we are finished. So we now have the limit as t tends to infinity, negative t to 0, 3x e to the u, negative 1 over 2x du, and I broke my little rule, but I'll fix it in a minute. When you do U subs, don't put those guys in for a little while. So it's going to be negative 3 over 2 e to the u du. Agreed? Negative 3 halves e to the u. Well, integrate that and you get negative 3 halves e to the u. If you return back to the x's, it's negative 3 halves e to the negative x squared, evaluated at x equals negative t to x equals 0. Plug in 0 here, we get negative 3 halves e to the power of 0. Take away negative 3 halves e, and if you plug in negative t in here, right, negative t squared is t squared, so it still ends up being negative t squared. So what we've got now is the limit as t tends to infinity, that's 1, so you get that, plus 3 over 2 e to the negative t squared. Now I'll do the brute force. Negative 3 over 2 plus 3 over 2 e to the minus infinity. Okay, e to the minus infinity. What on earth do you get with e to the minus infinity? 0 or infinity? What do you get with that guy?
0.
Right. You remember the make it look like that, easier to tell. So isn't the answer here negative 3 halves? Okay. So the left-hand side is cool.
Wouldn't the negative infinity be squared because of t squared?
Yeah, but if you do infinity squared, it's still infinity, right?
Oh, okay, okay.
Now, if you go the other direction, and I'm not going to do it, or maybe I will, I'll see. No, I won't do it. Can you just trust me that it ends up being positive 3 halves? It's very similar working. So what's the result? Well, the result in this case is the answer is 0. And no, that's not a contradiction. Can you imagine that the shape looks something like this? Can you see that all of this stuff cancels out all of that stuff? There's a lot of symmetry going on. So doesn't 0 seem actually quite reasonable when you think of it like that? Now, can we just pretend that that answer ended up being infinity? Well, actually negative infinity. And this answer here ended up being plus infinity. You are not allowed to join those together and get 0. You agree that that is mathematically not necessarily true. Don't think of these as numbers. Couldn't one of these infinities be a bigger version of the other infinity? Couldn't one of them be how many fractions there are in the world, and the other one be how many whole numbers are in the world, right? Could you imagine? Both are infinite, but isn't one a lot more infinite than the other, right? So that's why you're not allowed to do the just single integral thing, because they could end up cancelling each other out, which would be bad news all round if that happened. Where else shall we travel? Okay, one last question for today. Let's do this fella. And this fella has trig in it. And normally when I see trig, don't you just say it diverges because trig goes up and down and bad things happen and so on, right? But I think this one is strange enough that it might be worth trying out. So it's going to be the limit as t tends to infinity, 0 to t, sine theta, e to the cosine theta, d theta. What technique are we going to use to integrate this guy?
U sub
It is. What's the u sub going to be?
cosine theta.
Did you say theta there, Mia?
Yeah, I think I'm
Thank you.
you saying it. So yeah.
I got my first convert. I got somebody who said theta. You make me so happy. Sabrina, come on. What's that called?
Theta.
Thank you. Okay, so you differentiate, you get negative sine theta. You do a crossover. And then you divide both sides by sine 1 over, well, divide by minus sine theta essentially, to isolate the d theta. So this is going to be the limit as t tends to infinity. Since it's a u sub, I'll not put limits of integration in. So we have sine theta e to the u negative 1 over sine theta du. Essentially, we get a really nice integral, right? The integration is probably not that difficult. I don't think we've had any really horrible integrals yet. That becomes this fella. Which in turn, when you return them back to, in this case, the thetas, oops, I'm thinking ahead here. There we go. So it's going to be the limit as t tends to infinity of negative e to the cosine of t, take away negative e to the cosine of 0. And down to brute force, negative e to the cosine of infinity plus, well, cosine of 0 is 1, so that's e to the 1, which is e plus that. Okay. What do you think our conclusion is going to be, because there's an e to the cosine infinity going on here?
Is it that it diverges because
Yeah.
you can't find a cosine of infinity?
Pretty much, yes. Can't say it better. It diverges. So this one has also lived up to the, if you see a sine or cosine, it's probably going to diverge, right? But here's the proof of why it did. I was hoping that that one, you know, I can't think of off the top of my head, but I was hoping that that one might have came out in such a way that you got a number out of it and it converged. I mean, I'm pretty sure, you know, of all the functions in the world, isn't there probably at least a couple of trig functions that don't diverge, right? There's going to be some in there. Oh, a basic one, wouldn't tan theta work? Yeah, tan theta would work, because that would end up being sine over cosine. That'd be the log of a cosine. Oh, darn it, that wouldn't work either, because log of cosine infinity is still, I don't know. I can't think of any, but I'm sure there is some somewhere. So let's finish with a weird one. This thing's called Gabriel's horn. Look it up. Gabriel's horn has some weird properties. I want you to take, or imagine you take the function 1 over x. Nothing really remarkable about it. And you start at 1 and you integrate it. So if you find the integral from 1 to infinity of 1 over x dx, right, that guy, it becomes the limit as t tends to infinity of this guy. Probably one of the simplest type 1 integrals you could ever do, right? It becomes the natural log of x evaluated at 1 and at t. And it's the log of t, take away the log of 1. Right, brute force now. The natural log of infinity, take away the natural log of 1. The natural log of an infinitely big number is still infinite. Would you agree? And so this diverges. So this area in here is infinitely big. Okay, I can handle that. I've seen others that are infinite. It's infinitely big. So what's this Gabriel's horn thing? Well, you take 1 over x, you start at 1, but this time you rotate the entire curve about the x-axis. And when you rotate the entire curve about the x-axis, what you end up with is basically a shape that looks like this, called Gabriel's horn. Can you imagine it looks like a horn? And we are now going to find the volume of that horn. Now, you notice that this area here is infinite. We've just done it. So wouldn't you expect this to be infinite as well? Does that seem reasonable? Well, let's find out. Its volume is the integral from 1 to infinity, rotated about the x-axis. Well, isn't that pi f of x squared? Isn't that how you would get the volume rotating about the x-axis? So the volume is going to be the limit as t tends to infinity of 1 to t of pi over x squared dx. So far, so good. And that's going to be the limit as t tends to infinity of, let's kick the pi outside because it's annoying. And let's call that 1 over x squared, x to the negative 2, to make it easier to integrate. So the volume of this shape is the limit as t tends to infinity. If you add 1 to the power and divide by the new power, you get that. You then evaluate it at 1 and at t. To make it easier to calculate, I'm going to take that -1 power and return it back to being a fraction. So we're now going to go the limit as t tend to infinity of that guy minus pi over 1, which is basically that guy. And so it's going to be the limit as t tends to infinity, -pi over t plus pi. We'll do a brute force. Plug in infinity here. -pi over infinity plus pi. Would you agree that -pi divided by infinity is 0? So Gabriel's horn has a volume of pi. Now, how on earth can you have a curve whose area here is infinite, but whose volume is finite? The fact that that has got a finite volume, couldn't you fill that up with pi gallons of paint? But you couldn't paint the inside because its area is infinite. That is just weird. Right? What that tells us, it's in a branch of math called topology. It's telling us that we have to be really careful about our preconceived ideas of what is common sense, because some things lack intuitiveness. Intuitively, you think it's obvious that this should be true if that's true. And yet we found out that it isn't always the case, especially when things are infinite. To give you an example of a similar problem, do you know I can create a shape that has a finite area and an infinite perimeter? And you're probably thinking there can't be any such shape. Finite area, infinite perimeter. Here goes. Can you imagine that is an equilateral triangle? Would you agree that as long as you can enclose it inside a circle, would you agree that shape has a finite area? Right? Now, one in the middle, I guess, 1/3 of the length, you make 3 baby isosceles triangles whose lengths are 1/3 the side. On each of these, you do some more little baby isosceles triangles, 1/3 the length of them. On each of these, you do the same again. Can you imagine doing this like a fractal forever? Right, every little triangle has another couple of little baby ones, 1/3 the size of the one it came from. That shape has a finite area. Why? Because it's still inside that circle, right? It's got a fixed area, it can't be infinite. If you started at one corner and tried to walk along the entire shape, wouldn't the perimeter be infinite? Because isn't there an infinite number of little triangles that you have to traverse?